Stand in front of a mirror. Look at yourself. Now tell me, without thinking too hard about it, where is your reflection? If you're like most people, you'd say it's right there on the glass. That's where your eyes tell you it is. That's where you can touch it. Put your finger on the surface and the reflected fingertip meets yours exactly at the point of contact. Breathe on the mirror, the fog appears exactly where the image of your mouth was. The whole reflection has the height and width of the mirror itself. The image lives on the glass. That answer is wrong. It's not a little wrong. It's not wrong in some subtle philosophical sense. It's wrong by 2 feet, or 4 feet, or 20 feet, depending on where you're standing. Your reflection isn't on the glass. It isn't near the glass. It's somewhere behind the wall the mirror is mounted to. It's in a place you cannot physically reach. And strangely, nobody ever sees this clearly until somebody points it out to them. I'm going to point it out. But first, let me be fair to the wrong idea. I want you to feel comfortable with it, because the evidence for it is, at first glance, overwhelming. When you stand in front of a mirror, the edges of your reflection fit neatly inside the edges of the frame. If the mirror is 4 feet tall, your reflection is limited to a 4-foot window. If you smudge the surface with your finger, the image is obscured right where the smudge is. If you crack the glass, you see the crack running through your face. Every interaction you have with the mirror, touching it, cleaning it, breaking it, suggests the image is right there, on the reflective surface, glued to the silver like a photograph mounted on a wall. Your whole visual system is on board with this. When you look around a room, you don't feel any mystery about where things are. The lamp is on the table. The painting is on the wall. The mirror, you figure, is on the wall too, and so is the reflection in it. A painting on the wall is on the wall. A reflection on a mirror is on the mirror. That's just how surfaces work. So everyone walks around their whole life with this quiet assumption. The reflection is on the glass. It's a perfectly reasonable mistake. I made it myself until somebody walked me through the actual geometry. Let me poke a few holes in this idea, slowly at first, and we'll see if it holds up. Here's the first test. Close one eye. Look at yourself in the mirror with just one eye open. Notice exactly where your reflection appears. Without moving your head, close that eye and open the other one. Does the reflection stay in the same place? If the reflection were truly on the glass, it would stay put. When you close one eye and open the other, anything painted on the mirror, a smudge, a sticker, a piece of tape, doesn't budge. It's stuck to the glass. Your 2 eyes are looking at it from slightly different angles, but it's in the same location. Your reflection does something different. When you switch eyes, the image shifts a little. It shifts relative to the frame of the mirror. It shifts relative to any smudges on the glass. But it stays aligned with your real body. If you're wearing a red shirt, the red shirt of the reflection stays aligned with the red shirt of you, not with the mirror's surface. That's peculiar. That's your first clue. Whatever the reflection is, it's not glued to the glass. It's moving the way a real object at some other location would move. Specifically, it's moving like an object that's the same distance behind the mirror as you are in front of it. Here's a better test. Get a camera. One of the film cameras with a real lens, not a little snapshot thing. A lens you can focus manually. Stand in front of a mirror and try to photograph your own reflection. Focus carefully. What do you have to do? You have to focus the lens not on the glass itself, but on some point beyond the glass. You have to focus it as though your subject is far away, further than the mirror. If you focus on the glass surface, your reflection in the photograph comes out blurry. If you focus past the glass into empty space behind the wall, your reflection comes out sharp. This is physics you can test. Any photographer who has tried it knows it. The camera's lens has no opinion about what should be in focus. It just focuses on wherever the light is actually coming from. And the light of your reflection, it turns out, is coming from a point much further away than the glass. Try another one. Take 2 mirrors and face them toward each other, with yourself standing between them. Look into one. You see yourself. You also see yourself seeing yourself. And you see yourself seeing yourself, seeing yourself. The corridor of images stretches off, smaller and smaller, into what looks like an endless hallway. Consider this carefully. If your reflection were on the glass of the first mirror, and the next reflection were on the glass of the second mirror, and so on, the whole chain of images would be stacked like playing cards on top of each other. The 12th reflection would be in the same place as the first, just dimmer. That's not what you see. You see a receding tunnel. Each image is further away than the one before. The tunnel has depth. It has distance. The images are not on the glass. They are spread out along a corridor that stretches where? There's no actual corridor there. The mirrors are flat against the wall. The wall is solid brick or plaster. There's no room for a hallway to exist. And yet your eyes see one. Your brain sees one. If you could somehow walk into the mirror, you'd walk for a long, long way. The images are in a place that doesn't physically exist. We call this a virtual image. Virtual, meaning it's not really there. Light is not actually coming from that location. But your eyes construct the scene as though it were. So the reflection isn't on the glass. Where is it? Here's the answer, and I want to state it simply before I explain why. If you are standing 3 feet in front of a mirror, your reflection is 3 feet behind the mirror, which means your reflection is 6 feet away from you. Not 3. 6. Every reflection you have ever seen in a flat mirror has been twice as far from you as you thought. The image is in a location no physical object occupies, through the mirror, past the wall, in the neighbor's apartment, or the inside of the wall framing, or wherever the geometry puts it. That's where it lives. Let me show you why. Imagine a single ray of light, not a photograph, not a whole scene. One skinny little beam, like a laser pointer. This beam leaves your nose, travels forward to the mirror, hits the surface, and bounces off. When a ray of light hits a mirror, there is one rule it follows, and it's very strict. The angle it comes in at equals the angle it leaves at. If it hits the mirror going downward at 30 degrees from straight in, it leaves going upward at 30 degrees from straight in. Like a tennis ball bouncing off a practice wall, except much more precise. So one ray leaves your nose and bounces off the mirror. Another ray leaves your nose a little to the left, hits a different spot on the mirror, and bounces off at its own angle. A third ray leaves your nose, goes straight at the mirror at right angles, and bounces straight back the way it came. All these rays, having bounced, now head outward from the mirror in various directions. Some of them enter your eye. Your eye collects them, brings them to a focus on your retina, and forms an image. Here's the question. When your eye gathers those rays, where does it compute the light to be coming from? Your eye is a simple device, in a sense. It can't measure how a ray has been bouncing around. It just looks at the rays as they come in and asks, if these rays had been traveling in straight lines, without bouncing, where would they be coming from? Trace the rays back. The ray that bounced off the mirror at a 45-degree angle, if you extend it backward in a straight line, not along the path it actually took, but along the straight line it appears to be coming from, goes somewhere behind the mirror. The ray that bounced off the center of the mirror and went straight back, if you extend it backward, also points somewhere behind the mirror. And when you do this for every ray, when you carry out this exercise with pencil and paper, all those extended rays meet at a single point. That point is where your eye and brain agree the light is coming from. It's a point behind the mirror, at exactly the same distance as you are in front of it. It's as though there were a twin of you standing behind the wall, sending out rays of light, which then pass through the wall and reach your eye. There is no twin. There is no light behind the wall. The light is coming from you, bouncing off the glass and reaching your eye. But your eye has no way of knowing the bounce happened. To the eye, the light seems to be coming from behind the mirror. And so the brain constructs a world in which there is an object behind the mirror, a fake object, a phantom, a ghost that exists in a place where nothing physical can exist. That phantom is your reflection. Let me say why the geometry works out so perfectly. Imagine the photon of light that leaves your nose. It has to touch the mirror and reach your eye. Of all the possible paths it could take, the one it takes is the shortest one, the one that minimizes travel time. This is called Fermat's principle, after Pierre Fermat, a 17th century French mathematician who figured out that light always seems to pick the quickest path. When you work out the geometry of the shortest path from your nose to the mirror to your eye, you find the bounce point is exactly at the spot where the angle of incoming light equals the angle of outgoing light. That's the law of reflection, and it falls straight out of the principle of least time. And there's a beautiful consequence. If you extend the outgoing ray backward through the mirror, past the silvered surface, into the space behind, the extended ray hits the same point it would hit if the light had traveled in a perfectly straight line from a spot that's the mirror image of your nose, the same distance behind the mirror, directly opposite your real nose. Every ray you could trace from your nose through a bounce to your eye appears to come from that symmetric point. Not just one ray, all of them. It's a geometric inevitability. This perfect symmetry is what makes the reflection look like a full, three-dimensional scene. If only some of the rays converged to the symmetric point, you'd see a distorted image, smeared out, fuzzy. But every ray converges there. So the reflection is sharp, complete, and geometrically exact. It's your twin, pinned to a point in non-existent space with surgical precision. People have known this for a very long time. Euclid, in the 3rd century before the Common Era, wrote a treatise called Optics that described the law of reflection correctly. Heron of Alexandria, a few centuries later, used a principle like Fermat's to prove that light takes the shortest path from object to mirror to eye. By the time of Newton, the geometry of reflection was well understood. Newton's book, titled simply Optics, published in 1704, works all of this out in detail. Knowing the geometry and feeling the geometry are two different things. You can read Euclid and solve for the image position, and still, when you stand in front of a mirror tomorrow, you'll feel like the reflection is on the glass. The math and the sensation are two different creatures. The geometry tells you where the image is. The perception tells you where it feels like. And no amount of mathematical understanding quietly changes the feeling. I think this lecture is most useful not for the geometry, which was settled 2,000 years ago, but for making the feeling match the geometry. To look at a mirror and genuinely experience the reflection as being behind the glass. To see the parallax. To notice the camera focus. To catch your brain in the act of constructing a ghost. Why does the brain do this? Why does it trust rays it shouldn't trust? The answer goes back hundreds of millions of years. Every organism with eyes evolved in a world where light generally travels in straight lines. If light is coming from a certain direction, there's almost always an object in that direction, sending the light. Trees don't bounce their leaves off something before the light reaches you. Fires don't reflect off a hidden wall before hitting your eye. In the wild, backward extension of rays is a reliable way to locate things. Mirrors are a new problem. They're man-made, mostly. There are a few natural mirrors, a still pond, a piece of polished obsidian, a frozen puddle. But for most of our evolutionary history, our visual system never needed to deal with a surface that systematically bent light in a way that produced coherent fake images. So when a mirror does that, the brain just applies its old rule. The rays appear to come from behind the mirror, so the brain places the object behind the mirror. No question, no doubt, no hesitation. This is why no baby ever reasons its way past a mirror. No dog either. They bark at the reflection, sniff it, try to make friends with it. Babies do the same. It takes years of experience to learn that the person in the mirror is a reflection, and not a separate person living in a separate room through the wall. Even as an adult, you don't fully stop doing this. When you see something in the rearview mirror of a car, the thing looks like it's in its true location, with its true shape, at a specific distance behind you. It isn't. It's in front of you in some sense, bouncing off the rear view. Your brain just quietly puts it in the right mental location, even though the rays are coming from a different direction than the object itself. So, the reflection isn't on the glass. It's behind it. That much I've argued carefully. Let me go further, because there's a second belief about mirrors that almost everyone holds, and it's also wrong. Let me test you. If you raise your right hand in front of a mirror, which hand does your reflection raise? Most people say the reflection raises its left hand. That's what we were all told as kids. Mirrors reverse left and right. They show you a flipped version of yourself. Right becomes left, left becomes right. Textbooks say it, teachers say it, it's common knowledge, it's also wrong. Mirrors don't reverse left and right, they reverse front and back. Here's the clearest demonstration I know. Take off your wristwatch. Hold it out in front of you so you can read the face. The 12 is at the top, the 3 is on your right, the 6 at the bottom, the 9 on your left. Walk up to a mirror and look at the watch in the reflection. The 12 is still at the top of the watch's reflection. The 6 is still at the bottom. The 3 is still on your right. The 9 is still on your left. Nothing's flipped. Not left, not right, not top, not bottom. The watch in the reflection looks exactly like the watch in your hand, because you're looking at both of them from the same side. You didn't turn the watch around. Nothing needed to reverse. When you look at yourself in the mirror, the reflection looks different. The reflection's right hand appears on your left. Why? Because your actual right hand, your real, physical hand, is on your right. And in the reflection, your right hand is still on your right. It's on the same side of the mirror image as it is on you. There is no swap. The illusion of a swap comes from us imagining the reflection as another person. If somebody walked up to you from the other side of a glass door, a real person, facing you, their right hand would be on your left, because they turned around to face you. Our brains automatically compare the reflection to that kind of scene. And so we think the reflection has swapped left and right. A reflection doesn't swap left and right. It swaps front and back. Your nose in the reflection is pointed toward you, not away from you. That's the actual reversal. It's the one axis the mirror cares about, the axis perpendicular to its surface. Everything along that axis flips. Everything perpendicular to it stays put. If you're not convinced, try this. Write the word cat in big letters on a piece of paper. Hold the paper up facing yourself so you can read it. Now, without turning it around, press the back of the paper against your chest and walk up to a mirror with the printed side facing the glass. In the mirror, you can see the paper. The word cat is visible on it, readable, left to right, C-A-T. The mirror didn't reverse the letters. It showed you the paper exactly as it is, seen from the side that was facing the glass. But if you turn the paper around, facing yourself, and hold it up in front of the mirror, now the mirror shows the back of the paper. And if you had written cat in ink dark enough to see through the paper, the letters in the mirror would appear backward. Not because the mirror flipped them, because you flipped them when you turned the paper. The mirror just showed you the result. Mirrors are honest about what they show. They don't play tricks. They just show you what's facing them, reflected through the one axis perpendicular to their surface. We confuse ourselves by thinking of the reflection as a person when it's really a geometric transformation. While we're dispelling myths, here's another one. How fast is your reflection moving when you walk toward a mirror? Most people's first guess is the same speed you're walking. If you're heading toward the mirror at 4 feet per second, the reflection's heading at you at 4 feet per second. That's wrong. Because you're approaching the mirror at 4 feet per second, and your reflection is approaching the mirror at the same speed from the other side. So the two of you are closing in on each other at 8 feet per second. Your reflection is rushing at you at twice the speed you're moving toward it. If a housefly lands on a mirror, the fly's reflection meets it with apparent speed 0. But if the fly takes off and flies at the mirror, then in the instant just before it hits, the fly and its reflection close the gap at double the fly's airspeed. The mirror is a liar about distance. It's also a liar about speed. Every time. Let me throw in one more surprise about flat mirrors before we move on. Most people, if they had to guess how tall a mirror needs to be for you to see your whole body, would say about your height. If you're 6 feet tall, the mirror would need to be 6 feet tall. The mirror only needs to be half your height. Exactly half. Not a little less. Half. Find a tall mirror. Stand in front of it. Use a piece of tape to mark the highest point of your reflection and the lowest point. Measure the distance between the two pieces of tape. I will bet you a good dinner that the distance is half your height. It works no matter how close or far you stand. You can step up until your nose is at the glass, or back up until you're across the room. The mirror only needs to be half your height to show you head to toe. The geometry says so, and the geometry doesn't care how you feel about it. Why? Because the light from the top of your head bounces off the mirror at a point halfway between your head and the mirror's surface in the vertical dimension. The light from your feet bounces off at a point halfway between your feet and the mirror's surface. All the light that creates your reflection uses only the middle half of the vertical span. The top quarter and the bottom quarter are unused. This is why full-length mirrors in hotels and clothing stores are often shorter than they look. They don't need to be 6 feet tall. 3 feet, mounted at the right height, is plenty. Let me turn to the mirror itself for a moment. What is a mirror, really? At the atomic level, what's going on? For most of human history, mirrors were not objects people had easy access to. Early mirrors were polished metal, bronze, silver, gold, sometimes a still basin of water. Glass mirrors, as we know them, with a thin silver coating on the back of a pane of glass, became widespread only in the 16th and 17th centuries. Before that, if you wanted to see yourself clearly, you found a pool of water or a polished metal plate. And the image in a pool of water is a perfect example of the same physics. You lean over a pond, and you see yourself looking back up. Where is that image? On the surface of the water? Of course not. It's below the water, at a depth equal to your height above the surface. If you're 4 feet above the water, your reflection is 4 feet below it. The pond, if it were deep enough, contains a virtual column of ghost dew extending downward. And if the pond is shallow, the virtual column extends right through the mud at the bottom and into solid earth. The ghost doesn't care about obstacles. It lives in a mathematical location, not a physical one. Silver-backed glass mirrors work on the same principle. The silvering on the back of the glass is what actually does most of the reflecting. The glass in front is just a protective layer. Light enters the glass, travels through it, bounces off the silver, travels back through the glass, and exits. The silvered surface is where reflection happens. It's a thin film of metal, usually a few hundred nanometers thick, painted onto the back of the glass. At the atomic level, the reason metals are good at reflecting light is that they have free electrons. Electrons that aren't bound tightly to any particular atom, but that slosh around through the whole metal like a liquid. When a photon of light hits the metal, those free electrons immediately react. They move in response to the photon's electric field. And as they move, they produce their own electromagnetic field, which re-radiates the light back out of the metal. This is why metals are shiny. It's why silver, gold, aluminum all look like mirrors when polished. It's why rust, which is iron oxide and has no free electrons to speak of, looks dull. The reflection in a mirror isn't mysterious at the atomic level. It's just a dance of electrons sending light back where it came from. The location of the image, though, where the reflected rays appear to converge, is a geometric fact. It doesn't depend on what the mirror is made of. It depends on the mirror's shape. For a flat mirror, the image is behind the glass at the mirror image position of the object. For a curved mirror, it's somewhere else. The material doesn't matter. A polished sheet of aluminum produces the same image location as a silvered glass, given the same shape. A little aside for you. If you look very carefully at your reflection in a bathroom mirror, you can sometimes spot a second, fainter image slightly offset from the main one. This is because a glass mirror actually has two reflecting surfaces. The front surface of the glass, where glass meets air, reflects a small amount of light all by itself. Glass always does this. Even plain window glass reflects about 4% of the light that hits it. The back surface, where the silver is, does most of the reflecting. So you get two reflections, a strong one from the silver, offset behind the mirror, and a weak one from the front surface of the glass, offset a little less. High-quality optical mirrors, like those used in telescopes, put the silvered layer on the front of the glass instead of the back. These are called first surface mirrors. There's no ghost image because the front surface is the mirror. But the coating scratches easily because it's exposed. That's why bathroom mirrors aren't made this way. You'd scratch them down within a week with a towel or a fingernail. Here's something else worth noticing next time you walk through a city at dusk. The windows of a tall building, if they're flat glass, act like mirrors, especially when it's brighter outside than inside. You can see reflections of the buildings across the street in those windows. Where is that reflected building? Behind the glass, inside the office. But the office is full of desks and people. There's no room for a whole building to be in there. The reflection doesn't care. It occupies a virtual location that passes right through the office, through the far wall of the building, and out into the world beyond. If the building across the street is 50 feet away, the reflected version of it is 50 feet behind the window. The reflection extends through all the floors and walls and people as if they weren't there. Because, of course, they aren't in the space where the image lives. The image is in that non-existent mathematical place I keep talking about. It doesn't have to respect architecture. This is why city skylines full of reflective glass can feel disorienting. You're not just seeing the buildings. You're seeing the buildings and ghostly duplicates of them, projected into spaces where no building could be. And in some buildings where the glass is slightly curved, the reflections are distorted, stretched, shrunk, warped. The ghost versions of skyscrapers dance through phantom space while the real skyscrapers stand still. There is a special kind of mirror that does something truly strange. It's called a corner cube, or a retroreflector. You can make one with 3 flat mirrors placed at right angles to each other, like the inside corner of a box. Take the inside corner of a shoebox. Now imagine that all 3 inside walls meeting at that corner are mirrors. If you shine a flashlight into that corner from any direction, the light bounces 3 times, once off each mirror, and leaves going back in the exact direction it came from. Not the opposite direction. The same direction, but reversed. If the light came in from the upper left, it goes back out toward the upper left. If it came in from below, it goes back out toward below. Wherever the light came from, it heads straight back there. This has strange consequences. Bicycle reflectors work this way. So do the little reflective strips on road signs. The light from your headlights bounces off and comes straight back at you, which is why road signs look so bright at night. They're throwing your own light back at your eyes. On the moon, there are mirrors. In the late 1960s and the early 1970s, the astronauts from the Apollo program left retroreflector arrays on the lunar surface. Scientists on Earth bounce lasers off of them to measure the distance from Earth to the moon to within a few centimeters. A thin beam of light leaves a telescope, travels 250,000 miles, hits a small array of corner cubes on the moon, and bounces straight back toward the telescope that sent it. Any other kind of mirror wouldn't work. You'd have to aim a flat mirror with incredible precision, and the Earth and moon are both moving. The retroreflector doesn't care. Wherever the light came from, that's where it goes back. Here's a puzzle. If a corner cube sends light back the exact way it came, what do you see when you look into one? Where is your reflection? This is where it gets genuinely strange. In a flat mirror, your reflection is behind the glass at the mirror image position. In a corner cube, the geometry is different. Every point of view sends light into the cube. The cube sends it back to that same point. Light from your cheek returns to your cheek. Light from your chin returns to your chin. The only light that reaches your eye is light that came from your eye in the first place. So what do you see? You see your own eye, just your eye. A single dark pupil staring back at you. You cannot see any other part of your face. And if 2 people look into the same retroreflector, neither sees the other. They each see their own eye, nothing else. That's not a reflection anyone has ever described as normal. That's a mirror that refuses to show you anything but yourself, and really only the hole in the middle of your eye. Up to now, I've only talked about flat mirrors and corner cubes. There's a whole other world once you let the mirror's surface curve smoothly. Take a spoon. Look at the outside of the spoon, the convex side, the side facing down when you're scooping soup. Your reflection appears there, but it's shrunk. Your face is squashed into a dot. Tip the spoon, and the reflection shifts but stays small. Flip the spoon over. Look at the inside, the concave side. Your reflection is upside down. Your face is inverted, as if somebody hung a painting of you on its head. These are both mirrors, doing exactly the same thing as a flat one, obeying the law that the angle of incidence equals the angle of reflection. But because the surface is curved, every little piece of the surface bounces light at a different angle than the piece next to it. The rays that come off a curved mirror don't extend backward to a simple point behind the mirror. They converge or diverge in strange ways. When you have a concave mirror, a mirror that bends light inward, the rays from an object can actually converge to a point in front of the mirror, not behind it, in front of it. At that point, a real image forms. A flat mirror can't do this. A flat mirror can only produce a virtual image, a ghost, a thing that lives in a place where no object could actually be. A concave mirror can produce a real image, and a real image is genuinely different. Put a piece of paper at the location of a real image, and the image appears on the paper. The light is actually there, focused into a picture. You don't need an eye to see it. A photographic plate would capture it. A fly landing at that spot would be illuminated by it. The light is converging there, physically. A virtual image, you can't do any of this. Put a piece of paper behind a flat mirror. Well, you can't, because the wall's there. But if you could, there's no light. There's nothing on the paper. The image is an illusion of the eye, a construction of the brain, a place where light seems to come from without actually being there. This is the deep distinction in optics between real and virtual. A real image exists in space, composed of actual light, and anything light-sensitive placed at that location will detect it. A virtual image exists only in the interpretive apparatus of the observer. It's not even accurate to say the virtual image is at a location. The virtual image isn't truly at any location. It's only attributed to a location by a mind that thinks rays travel in straight lines. The moon seen in a puddle is a virtual image. The moon isn't down there under the water. If you reached into the puddle, you wouldn't grab a little moon. You'd grab wet mud. A magnifying glass held close to a book produces a larger virtual image of the print. You can't catch this image on a screen. Held further away, the same magnifying glass produces a real image, upside down, which can be projected onto a screen. This is how early photographic cameras worked. A lens focuses a real image onto a photographic plate, and the plate records it. The distinction between real and virtual images is as close as optics gets to a statement about what really there means. Real images involve actual light arriving at a location. Virtual images involve light that appears to come from a location, but doesn't. And here, finally, is where I want to land. Every reflection you have ever seen of yourself, in a bathroom mirror, in a store window, in the still surface of a pond, has been a virtual image. A ghost, composed of nothing, located in a place where no physical thing could be. That ghost has followed you every day of your life. It has imitated every movement, aged alongside you, seen you at your best and worst, and it has not once existed. You have looked at yourself thousands of times. You have never actually seen yourself. Because what you see in a mirror isn't you. It's an interpretation your brain performs on light that bounced off a thin layer of silver. The actual you is on this side of the glass, facing the other way, looking at a phantom. Sit with something else for a moment. Every other thing you see works almost the same way. The chair across the room, the tree outside the window, your own hand in front of your face, these are all known to you, only because light from them enters your eye and your brain builds a picture. In a strict sense, you do not see the chair. You see your brain's guess about what's making the light behave the way it's behaving. A mirror is special only because the brain's guess is provably wrong. The guess places the reflection behind the glass, and we all agree there is nothing behind the glass. The reflection is not where the brain says it is. But you can't easily say the same thing about the chair. The chair is, as far as we know, really there, roughly where your brain places it. Still, both are interpretations. Both are constructions from rays of light. The mirror just lets us catch the construction happening in a case we can disprove. So every mirror is a free demonstration of how perception works. A little window into your own visual processing. A place where you can see your brain doing its job and making an honest, geometrically justified mistake. You walk past a mirror tomorrow morning and you'll see yourself. The reflection will be behind the glass. You will experience it on the glass. You will probably, out of habit, think the reflection is at the surface, not behind it. The geometry won't change your feeling. But now you know. You know the reflection is twice as far from you as it appears. You know the twin on the other side is a ghost made of nothing, in a place that isn't there. And you know that every other thing you see is a construction of a similar kind, built by the same brain, trusted to a degree that mirrors ought to make us question. That's what I want you to take with you. My question for you is this. The next time you catch your reflection in a window, a car's paint, a still glass of water, a polished spoon, anywhere at all, I want you to really look at it. Try to feel where it is. Try to sense its location in space. And then tell me, can you, with practice, make the reflection feel like it's behind the glass instead of on it? Can you retrain the feeling to match the geometry? I've tried, and I'm not sure you can. But I'd like to hear whether you succeed.